Good evening, everyone. Hopefully you can hear me. I would like to introduce myself. I'm Dr. Kirsten Mackay, and I am chairing this session of the third Nuclear Masterclass webinar. For this evening's event, we are joined by Howard Wilson, who is the Director of Science and Technology for the STEP programme, which is the Spherical Tokamak for Energy Production. Tonight, he's going to be explaining this exciting project to us and talking us through the process that powers the sun and how we bring it down to Earth. So I will hand over now to Howard for his talk.
Good evening, everybody, and thank you for this opportunity to tell you a bit about fusion, a bit about the science of fusion, and a bit about how we are aiming to deliver it, and in particular, how we're aiming to deliver it in the UK with the so-called STEP project, that's Spherical Tokamak for Energy Production. So this is an outline of my talk. I will start by introducing what is fusion, what is fusion energy, where does it come from? Then we'll look at the conditions that we need to try and achieve to make fusion happen, and we will find that they're quite extreme conditions that we need to achieve. We will then go on to look at one of a number of different ways of achieving fusion conditions, in particular the tokamak. And then the spherical tokamak for energy production is a particular design of a tokamak that we're exploring here in the UK, and I'll describe that, and then I'll finish with some conclusions. So first of all, what is fusion? So let me start quite technical. And for those of you who are A-level students, you may be familiar with this. Those of you who are GCSE students, you may be about to be familiar with it, but I'll give you a simple picture later on. But let me start off with a technical picture of where fusion comes from. So here we have a figure, a graph that shows what's called the nuclear binding energy per nucleon. Now, let me just break that down. So the nuclear binding energy is the energy that it takes to bind together the nucleons. So the nucleons are either protons or neutrons that make up the nucleus of an atom. So the positive bit at the center of an atom. Each proton or neutron is known as a nucleon. And the nuclear binding energy per nucleon is suppose you take a nucleus and you split it up into its constituent parts. That's the binding energy is the energy required to do that, and then you divide that by the number of nucleons, number of protons or neutrons in the nucleus. And if you look at that energy as a function of mass number, so this is really the different elements in the periodic table coming along here, you find there's a maximum, and that maximum is what we're working towards to release energy. So any element that's bigger than maximum, which is Fe, and Fe is the chemical symbol for iron, of course. So any element that's heavier than iron, the binding energy goes down as you increase the mass. So the really heavy ones, if I take these and I split them, the binding energy per nucleon goes up, and that means you release energy. So anything at this heavy end, you split it, it throws energy out. And that we already tap into that with for energy production with the so-called fission process, and that's the conventional way of producing nuclear power. Fusion is a nuclear energy source, but it's the opposite of fission. Fission will happen as long as you put a critical mass of the substance together. Fusion is what happens down this end. So again, you see the lighter elements. If you can fuse two elements together and make a heavier one, you also get an increase in the binding energy per nucleon. So you also release energy. And again, anything lighter than iron, if you fuse it, it will generally release energy. And so this is the fusion process that we're trying to make happen. It's much more difficult than the fission process, because with fusion, you have to force together these nuclei sufficiently close for them to fuse. They're both positively charged. They don't like being forced together. And so you've got to put a load of energy in to push them together sufficiently close. When you do that, you get much, much more energy out than the energy you have to put in to release that energy. The challenge with fusion energy is getting them to fuse, getting those conditions right to fuse. And we're going to look at that later. But let's just zoom in now on the process we're going to look at. So I'm going to zoom right in at the bottom end of this graph in the next figure and look at the very lightest elements. And in particular, I'm going to be looking at hydrogen, but not hydrogen itself, two so-called isotopes of hydrogen. So these are heavy forms of hydrogen. So hydrogen is one proton and one electron going around it. And you're all familiar with hydrogen in nature. A heavy form of hydrogen is something called deuterium. And to get deuterium, you add a neutron to the proton in the middle of the hydrogen. So you'll see deuterium has got a nucleus, it's got a proton in the center and a neutron, and still one electron going round. Now, it's this electron which gives an element its chemistry. And because the deuterium and hydrogen both have one electron and one proton, they have very similar chemistry. So they're very similar chemical things, but we call it a different isotope. So chemically, it looks exactly like hydrogen, but it's heavier because it's got another neutron. Neutrons and protons are about the same mass. They're a little bit different, but only a tiny bit different. And so this thing is like a heavy hydrogen. And then there's an even heavier hydrogen called tritium, and that's got two neutrons and one proton. Still one proton, one electron, so it's still hydrogen-like, but it's another isotope, an even heavier one called tritium. And that's these two things down at the bottom end of this table here. So H2 is another way of writing deuterium. H3 is another way of writing tritium. And the reaction that we're going to look at is fusing together the hydrogen, the deuterium and the tritium. So this is the reaction we're going to look at. Deuterium, which is one proton and one neutron, tritium, one proton, two neutrons, and they will fuse together, if you get the conditions right, to give you helium. And you see helium sitting up here. Look at all this energy that's released. It's a massive spike. Helium is really nice because it sits at a local peak in this nuclear binding energy per nucleon. And so it gives helium and this thing called a neutron. So if I count up my number of nucleons here, deuterium, we've just looked at it, it's got one proton, one neutron. If I look at this figure, it's got a binding energy per nucleon of 1, but it's got 2 nucleons, so we have a binding energy of 2 in these fancy units of energy, but don't worry about what they mean. But I thought I'd better put it in because you'd never have a number without units. So this is just a unit of energy. The tritium has got 1 proton and 2 neutrons, so 3 nucleons, and it's got a binding energy per nucleon of about 3. So 3 times 3 gives you 9 fancy units MeV. So the binding energy of my starting products is 11, if I add them together. My helium is way up here with a binding energy per nucleon of 7, but helium is 2 protons, 2 neutrons, so 4 times 7 gives me 28. I take the difference of 28 from 9 and 2, and I get about 17. The actual answer is 17.6. Of course, the neutron itself has no binding energy because it's already split down into its nucleon, so that's a 0 there. And so this is the energy that we're looking to release, and this is the energy that we're looking to tap into for fusion. If you didn't like that argument, there's a much nicer one, a much simpler picture, because this can all be understood in terms of the mass as well. And a very famous equation, E equals mc squared, that Einstein taught us over a century ago. And what does E equals mc squared mean? Well, E equals mc squared. E here is the energy that's released when you convert an amount of mass, m, into energy. And c here is just the speed of light, a huge number because the speed of light is fast, and you square it to multiply this. So a very small amount of mass loss gives you a big amount of energy. And if you weigh the deuterium and the tritium that you start with, you find that it's slightly heavier than the helium and the neutron that you end up with. So you've lost some mass, and it's basically that mass which is converted to energy through E equals mc squared. So if you didn't like that binding energy argument, just think of it in terms of Einstein's famous equation. So fusion, we know it works because you look up at the sun, and it's been a sunny day, I think, over most of the UK today. You look up at the sun, and that sun is being powered by fusion. It doesn't just power our sun, it powers all the stars. That's actually fusing through straight hydrogen, not deuterium and tritium. We'll look later at why we have deuterium and tritium rather than pure hydrogen. So we know it works. The challenge is how to, and we know the conditions that we have to get to make it work. In particular, we need to get conditions like the center of the sun, but actually we need to go beyond what happens at the center of the sun. We'll see later we need a temperature actually 10 times that at the center of the sun, around 100 to 200 million degrees Kelvin. But if we get those conditions, and we use the deuterium and tritium instead of hydrogen, which turns out to be an easier fusion reaction to make than just pure hydrogen. So we're going to take our deuterium and tritium, we're going to put them into some chamber, which we're going to look at later. Don't worry about what that is for now. We'll put them into a chamber, and we get the conditions right, including this temperature. They will fuse to give us helium and neutron. And these come out with huge amounts of energy. They come flying out from the reaction. 1/5 of that energy is held in the helium, and 4/5 of it is held in the neutron. So this is what I need you to remember now for the rest of this talk, that we're going to take deuterium and tritium as the starting points. We're going to fuse them, and they're going to give us helium as a product and a neutron as a product. 340,000 megajoules of energy. That sounds like a big number, but what does it mean? This comes out of 1 gram of fuel. So 1 gram is about the smear of butter. It's about how much a smear of butter on your toast would weigh. 340,000 megajoules of energy. If I did my calculation right, I've just bought an electric vehicle because I'm fancy and trendy. And I worked out how far I could get in that electric vehicle. And I could go more than the distance to the moon based on 1 gram of fuel. This is why fusion is so cool. This is why we want fusion to work. And this is why it's so valuable for sustaining our energy in the future. So deuterium and tritium sound like very exotic elements, very exotic materials that you don't come across in everyday life. And if you want to power the world, you better make sure you have a good supply of fuel. Actually, deuterium is plentiful. It sounds exotic, but every 6,000 hydrogens is in fact deuterium. And if you think about all the H2O, all the water that there is in the sea on our planet, there's absolutely tons of deuterium in the world. Tritium, though, is not a stable nucleus. It does decay, and it decays with a half-life of about 12 years, meaning if I have a jar of tritium and I close the lid and I go away and come back 12 years later, half of it will have decayed into something else, helium-3 actually. And so tritium, there's not much tritium around because it's constantly decaying. That then creates a problem. However, we have a solution. We can manufacture that tritium in place. And so the way we imagine doing it is we imagine you need an initial amount of tritium. So you've got to get an initial amount of tritium from somewhere, and you take your deuterium, you put it into this chamber, this plasma chamber, which we'll come to in a minute. We make our fusion reactions, we get helium. Remember that helium has got 1/5 of the fusion power. It's really fast, really energetic helium. And we call energetic helium a fancy label. We call it an alpha particle. So you'll hear me sometimes call this the alpha particle. Sometimes I'll call it helium. They're the same thing. The only thing about an alpha particle is a helium going very fast. This helium also gets trapped in that chamber. And that's a good thing because it gives up its power to the deuterium and tritium and keeps it in this hot state. So you've got to get the thing going, first of all, with a high heat source. But once it's going, if you get the conditions right, it's self-sustaining. This helium will give up its energy to the deuterium and tritium here and keep it hot. That's a good thing. So that's 1/5 of the fusion power. The other 1/5 of the fusion power, 4/5 of the fusion power, comes out in the neutron. You catch that in a blanket that's arranged around the chamber. And that blanket does three things actually, but let me focus on 2 of them. 2 things. One is it stops that neutron. So all that kinetic energy that neutron has had is given up to the blanket and makes it hot. You can then put a coolant through that blanket, let's say water, for example. You could use other coolants. You put water through there, the hot blanket converts that water into steam, that use steam to drive a turbine, put power on the grid. So that's the first job there. But the second job is if I put lithium or a lithium compound into here, the neutron will react with that lithium to create a bit more helium again and key the tritium. So you capture that tritium, you take it out of the blanket and you recirculate it around and put it back into your plasma. So we call this closing the fuel cycle, creating as much tritium here as we burn here to be able to sustain the reaction. This blanket is a really fancy thing. Nobody's ever built one in the world before. And so building something like STEP, this is a key part of it. How do we build that blanket? And there's some good questions that you could ask about that. So let's look at the benefits of fusion as a power source for society. First of all, you saw no carbon in there. So there are no greenhouse gases associated with it. All it produced was the helium, which makes you talk with a squeaky voice, put it in party balloons, etc. Very valuable commodity, but actually there's not very much of it produced anyway. Important point is it doesn't contribute to the greenhouse gases. It's safe. We're going to find fusion is a really difficult thing to do. So if anything goes wrong, it will just go out. You can't get a runaway reaction. It's reliable. You can turn it on no matter what the weather conditions, no matter whether it's dark, whether it's light, whatever. So you can power at will. It's sustainable. We have plenty of fuel. Let me just give you an example of the idea of how much fuel we've got. So really the fuels, although the reaction is deuterium and tritium, the raw fuels that we're putting in are deuterium, which we can get from seawater, for example, and lithium, which we can mine. And you all know about lithium. It's all in your mobile phone batteries now, or this laptop battery. And there's a really nice little quote. If you take the deuterium nice little fact. If you take the deuterium in a bath full of seawater and the lithium in one or two laptop batteries, for example, and instead of having a bath and powering your laptop, you instead do fusion. If we could do fusion, those would give you all the electricity that you need for your lifetime. So it's clearly sustainable. There's clearly plenty of fuel out there. And it's very energy efficient. It's very, it's very dense. And so it doesn't take up great swathes of land that you might want to use for other things like growing crops, for example. So there are lots of benefits. I haven't mentioned waste on here. Now, there's no waste with the reaction itself. As I said, it just produces the helium and a neutron. Where the waste comes in is that neutron will fly out and it will collide with whatever materials that you build your reactor out of. And so there is some low-level waste that's produced because of that interaction of the neutron with the materials. But the important point is that A, it's low level, and B, it's dependent on the materials you build the reactor out of, your fusion reactor out of. So if you can design some fancy materials, and there are fancy steels that you can do that are so-called low activation ones, you can further minimize that waste by materials research, for example. Nothing has no waste. Everything has waste associated with it. And it's important to recognize that and have a solution for managing it. So now let's look at the conditions. So the conditions are measured by something called the triple products. And as the name suggests, it's a product of three things. First of all, the density of the fuel, so the density of the deuterium and the tritium. So there's a little equation here that says my fusion power that comes out is proportional to the deuterium density, Nd, and the tritium density, Nt. And that's not surprising. The more dense your fuel, the more they're likely to collide into each other. So it depends on the density of the fuel, like the density squared, basically. And basically, the higher the density, the better. There is an optimum fuel temperature, which I'm going to call T. Now, that comes in through this thing, which is like the cross-section for the reaction. We call it the reactivity, and it's a probability that two particles will come together sufficiently close to give you a fusion reaction. And as I said, we need to work really hard to get them to come close. One way to do that is to heat them to really high temperatures. And if you heat them to high temperatures, they'll jiggle around faster and faster and slam into each other sufficiently hard that they will fuse. So if you look at this thing called the reactivity, it naturally depends on the temperature. And so here's my deuterium-tritium curve, and you'll see that it hits a maximum. Again, I've got these fancy electron volt things here. These are kilo electron volts. So there's 1,000 kilo electron volts in one of those mega electron volts, MEV things I said before. It's just a measure of temperature. And if you want a fancy dandy conversion factor, 1 keV, 1 kilo electron volt, is about 12 million Kelvin, or like 10 million Kelvin, if you like. So this 10 keV here is about 100 million Kelvin. So you'll see the DT cross-section hits a peak at about 200 million degrees. And so that's why we're aiming for this temperature of 100 to 200 million degrees. It's where this broad peak in the cross-section is and where we get a maximum of the fusion power. These are two other fusion reactions you might consider, deuterium against deuterium and deuterium with helium-3. And you can see why now we're choosing deuterium-tritium. You see that there's like an order of magnitude, it's a logarithmic scale, order of magnitude difference in this cross-section and therefore the fusion power that you get out. So we have to reach temperatures of 200 degrees. I know I've only done two from a triple product. I'm going to come back to the third in a moment. So we have to reach, but I just want to take a little bit of an aside and look at the consequences of going to 200 million Kelvin, crazy temperatures. If you take any material to 200 Kelvin, it's in what we call the plasma state. So I just want to spend a couple of minutes talking about the plasma state, because it's what I spent most of my research career doing since I was sort of in my early 20s. And you can think about it in terms of the states of matter that you're more familiar with. So you can take water, and as a solid state, it's ice, and you put energy in. So you heat it, for example. It liquefies, becomes its liquid state, water that we're familiar with. I've taken a little bit of artistic license here. And if you heat it further, you get steam. I know this isn't quite steam, but it's a nice picture. You get steam, which is a gaseous form of water. Now, suppose I keep putting energy in, I keep heating it. Remember that your water is H2O, so it's molecules of two hydrogens and oxygen. Now imagine heating it really high and those molecules crashing into each other. The hydrogen and the oxygen will split apart from each other and you'll get individual hydrogen and oxygen. Then you'll get, and then if you keep heating it, those individual atoms, the electrons will start getting bashed off the nuclei and you're effectively boiling off your electrons from your nucleus. And so rather than having a gas of neutral atoms or molecules, you will now have a gas of positively charged ions and negatively charged electrons. And of course, they now feel each other because of the electric fields between them, because they are one is an electron with negatively charged, one's a positive charge. The opposite charges will attract, like charges will repel. So that's a different way that those particles will interact with each other. It's the way neutral gas particles interact with each other. And you get a whole range of different phenomena, just as you get different phenomena between solids, liquids, and gases. A plasma, again, is different. And so we refer to it as the fourth state of matter. And in nature, the closest thing we have to us is typically a bolt of lightning. Fire is a very poor quality plasma, but it's kind of a plasma. Most plasmas on Earth are made by us for various technological applications. Go away from Earth, pretty much everything is in plasma state. The sun and the stars, interstellar medium, everything up there pretty much is dominated by the plasma state. So it's abundant in the universe, fairly rare here on Earth, but we need to make this plasma state in order to make fusion happen. This is just a picture of the sun. Sun, as I said, is a plasma. And it shows you the complex behavior you can get. Look, all these striations of stuff. This is absolutely fascinating plasma physics, and people still don't fully understand this. So if you're interested in plasma physics, solar plasmas are a great place to go. Fusion plasmas are a great place to go. Astrophysical plasmas are a great place to go. But there's a lot still to understand in plasma physics. It's very complicated, and the way the plasma interacts with the electromagnetic fields is really interesting. It's a gratuitous pretty picture. Let me get back to the point though. So I said triple products. We've done density, get it as high as you can. Temperature, try and hit the maximum. The other one is a little bit of a subtle thing called the confinement time. The confinement time measures how good your bottle is at holding in your fuel. Before I define it a little bit more clearly, let me just introduce now why this triple product is important. The triple product takes the density, the temperature, this confinement time, which we're going to talk about later, and though multiple of those three things is the triple product. And Lawson, UK guy, almost a century ago, or probably a century ago, almost a century ago, came up with this with the fact that this triple product had to exceed this big number. And when you do that, that's what you're trying to get for the fusion conditions. So this is what we're aiming for fusion conditions. And we'll look at it in a bit more detail shortly. Let's look at this confinement time, though. What is the physics of the confinement time? And I don't want to talk about plasmas and heating and power and things. I want to talk about a bucket of water, because you can understand what we mean by a bucket of water. And I'm going to talk about the confinement time of a bucket of the water in the bucket. If I have a perfect bucket, that water will just sit there. That has an infinite confinement time. The water is confined in the bucket for as long as I like, as long as you neglect evaporation, etc. Now, let me suppose that I put holes in that bucket. That now becomes a leaky bucket, and the water will leak out. And the rate of leakage of the water is related to the confinement time. In particular, the confinement time is the time taken for about half of that water to leak out. So clearly, the more leaky the bucket, the faster the water leaks out, and so the shorter the confinement time. So a confinement time measures how leaky is your bucket for water. For a plasma, what we're trying to do is try and get a certain amount of thermal energy. The density times the temperature, that's your thermal energy held in the plasma. So in the plasma, we're trying to hold the thermal energy there. So think about the thermal energy as the level of water in of the bucket. That's the analogy that we're going to be making, just to orientate you why I'm talking about buckets. Now, of course, I can fill that bucket at the same rate as the water comes out. I can have a tap and be pouring water in it at the same rate that water comes out, and that allows me to hold the water at the same rate indefinitely, as long as I keep putting water in. Going back to my analogy, if this is my thermal energy in a plasma, it will leak out my bucket. I have to put heating power in order to be able to keep it sufficiently hot, sufficient thermal energy to make the fusion energy happen. But now think about that. If I have a really leaky bucket, that says two things for me. One is I need to put lots of water in to keep it the same level. That's not good, because I'm paying for all this water I'm putting in. But B, this is going to make an enormous mess. Water is going to go everywhere. Similarly, with the thermal thing, if I'm trying to hold my thermal energy at the same level to keep my plasma sufficiently hot, I've got to power it at a certain level, and that costs me money. That's not good if you're trying to make money out producing electricity. So you don't want to put a lot of power in to hold the thermal energy at the same level. Plus, whatever I put in is going to leak out. So the more I put in, the more will leak out, and the more energy I have to handle in the exhaust system, and that's very difficult. So this confinement time is a key thing. So now let's look at the conditions. How do we achieve the conditions? And I'm going to look in particular at the tokamak. And we are going to, and in a tokamak, we hold on to the plasma, because we know to call it a plasma now, the deuterium and tritium in this plasma state, 200 million degrees. We're going to try and hold it away from material walls, because material walls don't want to be at 200 million degrees, using magnetic fields. So you can imagine a magnetic field like this, pointing in this direction, say, and you can imagine my particles in a plasma, which I've just drawn as a cylinder here. They all spiral because they're charged. They can't readily move across the magnetic field lines. They can readily move along them, but they can't move across them. There's a so-called Lorentz force that keeps pulling them back. And that means they spiral around the magnetic field lines like this. So that holds them away. If I imagine having a cylindrical can in here to hold the whole thing together, it would hold them away from the walls of the cylindrical can, but clearly they all leak out the ends. So a way to get around this is just to loop the whole thing round and connect those two ends together. If we do that, that gives us the basis of a magnetic confinement system. And there are a number of different magnetic confinement systems. And I should say other confinement systems are available, the so-called inertial confinement as well. I'm happy to take questions about that at the end, although it's magnetic confinement and tokamak's the thing that I know most about. But please do ask questions if you're interested in to know a bit more. In a tokamak, we are looking to make the plasma go round in a ring like this. We do that by making the magnetic field go round in a ring like this. And so to get that magnetic field to go around that, we have these D-shaped coils. So these blue coils here, and we put current through those coils. And by putting currents through each of those coils, we make a magnetic field line that goes round in a circle like this, like where the blue arrow is going. And that gives me my basic magnetic field for confining the plasma. Turns out that's not quite enough. And we need another component of the magnetic field that goes this way round. So because there's two components of the magnetic field, we give them two names. This one we call the toroidal component of the magnetic field. This one we call the poloidal component of the magnetic field. And we create this poloidal component of the magnetic field by driving a current through the plasma. And we do that from a solenoid in the middle. We ramp the current through this in the solenoid. That ramping the current through the solenoid means that it acts a bit like a transformer, with the solenoid being the primary of the transformer and the plasma being the secondary. And ramping the current in the primary induces a current in the secondary through Faraday's law, for example. And so that gives us the current and then gives us these two components of the magnetic field, which hold the plasma in this sort of car tire donut type shape we call a torus. These poloidal field coils aren't essential to the confinement, but they optimize the confinement. They make the cross-section of the plasma D-shaped rather than circular, for example. So this is just a cartoon sketch, of course. This is the world's most advanced tokamak, or was the world's most advanced tokamak, called JET. It's down here in Oxfordshire, about 100 yards away from where I'm sitting now, 100 meters away from where I'm sitting now. You can see the size of the thing from this little guy down here. He's not a little guy, he's a standard size guy. So you can see the scale of what the JET tokamak looks like. So let's look at the progress in fusion power over the years through the tokamak. So this is just the tokamak. So I'm looking at the triple product. This triple product here is measured in factors of 10, going from 0.001 here. Oh, I've got my units wrong here. This is 0.0001, 0.001, 110, etc. These are factors of 10, okay? And temperature in these kV units, fancy kV units, the center of the sun sits here, just to orientate you, about 2 kV. I can put two green lines on here. This one here, I'm trying to get to what we call physics break even. Physics break even means I get the same amount of fusion power out as the power that I put in to create the conditions for fusion. Ignition here, ignition means I don't need to put any power in to get the fusion conditions. All of the power comes from that helium, the helium that we produce in the reaction, the alpha particle. Remember that it produces the 1/5 of that takes away 1/5 of the fusion power and goes back into the fuel. The whole thing is sustained by that if we can get to this condition. So this is what we're aiming at, this kind of region up here, where we don't need to put much power in ourselves other than to start the thing up, and it'll all be self-sustaining. So where are we? Well, T3, tokamak was a Russian invention, and T3 was the first tokamak back in the 1950s, so 75, 80 years ago, T3. And it was way down, a factor of 10, 100 down in temperature, and a factor of 10, 100,000, 10,000 down on triple product. Way off. Sounds like that's not an exciting thing, but at the time, it was revolutionary, and it came the closest to when anybody had got to fusion conditions. That led to the rest of the world rushing out and building tokamaks. So these are tokamaks around the world. Aztecs was in Germany, TFR was in France, PLT I think was in the US. And through the 1970s and 80s, they immediately gained a factor of 10 in the temperature and a factor of almost 100 in the confinement time, for example, and other triple products. Then in the 80s and 90s, you see jets. Just closed down now. It's been around since the early 80s. D3D is still operating, been around since the mid 80s. Aztecs Upgrade, I think was here. I don't see Aztecs Upgrade. Pretty sure that came on. Oh, there. Aztecs Upgrade came on in the 1980s, in this period as well. Still operating now. TFTR was a US tokamak. It's closed down. And Altor C was a US tokamak. But now you see another factor of 10 on the triple products, but critically, already, this is 30 years ago, we were hitting these temperatures. The temperature is not the challenge. We can do the temperature. It's getting the triple product, which means getting the confinement time, which means making your magnetic field not leak the power. Okay, that's the challenge at the moment, is trying to improve this confinement time. So most recently during the 90s, same machines you'll see here as here. Now we're pushing up against break even. And that's how far we have come. We have come so close, and this is why we are now entering what we call the commercial era of fusion, where we're starting to get into the conditions which are power plant relevant. Here's a recent record. So Jet, full of records. I say it closed down in 2023, and in that final year, 2023, in its final few operations, it got the world record for the amount of fusion energy produced, so 69 megajoules. Only over 5 seconds, but that is significant. This is just the inside of Jet, by the way. It has beryllium walls on the inside and a tungsten, what we call the tungsten diverter. I'm going to come to that in a moment. So key records, which give people confidence to go and build fusion power plants, and that's why fusion is now seeing a lot of investment. So what next? So back to this diagram. To go up in confinement time now, we think we've done the best that we can with these tokamaks. And so to get a better confinement time, we're going to make it bigger. A bigger device just means it takes longer for the energy to get out. And so this is what ITER is based on. It is basically Jet scaled up in linear dimensions by a factor of 2, so volume increased by a factor of 8. This is the scale of ITER. So you can see these cars and things down here. It is a big industrial site. So this is fusion at the industrial scale. And its aim, with 7 partners from around the world, huge tens of billions of pounds budget, its aim is to produce 500 megawatts of fusion power from 50 megawatts of heating power. That ratio we call capital Q, so it's aiming for a Q of 10. And it is designed as an experiment, not as a demonstration, but it's designed as an experiment to demonstrate the science, to ultimately demonstrate the science and much of the technology associated with fusion. So in the last 5 or 10 minutes, I just want to look at STEP. What is STEP? Why is STEP such a big deal? Well, STEP is looking at a more compact version of the tokamak. So remember the diagram that I showed you and what we call the conventional tokamak, the jet-like tokamak. The toroidal field was created by a bunch of D-shaped coils. In a spherical tokamak, you replace all those D-shaped coils by a single column going up the center. So it's a conducting column. In the case of mass upgrade, our spherical tokamak here in the UK, it's a single column of copper, and then some return limbs coming round. So you can see these form what is effectively your D-shaped coils to create the toroidal field. But a big advantage of that is it means that your hole in the middle is much smaller, and it means your radial build is much smaller, and you have a much more compact device. And we think that will lead to a lower cost option for producing power. It's called a spherical tokamak because although it's still a torus, not a sphere, it's still a torus, toroidal thing. If you think about it looking like a chord apple, which is also a torus, a chord apple looks like a sphere. So the whole thing looks like a sphere. If I was standing in here, I'd be about this big. Okay, just to give you a sense of the scale for mast upgrade. This is a plasma, an actual plasma from mast. And when you see these wispy filaments, they're associated with the turbulence in the plasma. That's throwing plasma and energy out into and getting lit up by neutral particles outside. And that turbulence is what causes the leakiness. If we didn't have turbulence, the magnetic field that we impose, we're much better at holding onto the plasma. We'd have a much longer confinement time, and we'd have got to those fusion conditions decades ago. Understanding this turbulence is really key. So understanding why these wispy filaments form is key. And what you'll see in a moment there, bet you're worried because my voice had gone, there you saw it go really sharp and those wispy filaments stopped. Now this is on a repeat, and I repeat it after they go sharp. And what's happening there is the turbulence is being suppressed right at the edge. So we can see the plasma doing it. And actually the plasma does it itself. We think we understand it, but it only suppresses the turbulence right at the edge. And you get big pressure gradients at the edge as a consequence. You get like an insulating jacket around the plasma that it forms itself. And that keeps all of the center hot. The other thing I want to highlight here before I go to the next video is this ring, this bright ring. This is effectively the exhaust pipe of the tokamak. So all the heat and particles are coming out from the hot center out to the edge, and then they get funneled down to the bottom and up to the top into these regions here. This is a so-called diverter. I haven't got time to talk to you about this now, but if you want to ask me about it, Mast Upgrade has got a really fancy diverter where we manage this heat. It's the only one with a big box like this, and this could be key to be able to build a compact thing. There's another interesting piece of plasma physics I want to show. If I go to the next slide, which basically is going to show that video run a little bit longer, goes to this sharpness, and now watch, bang, you get this huge ejection of big filaments. These are called edge localized modes or ELMs, and these can do serious damage to your vessel. I get excited because it's really exciting plasma physics. The engineers get worried because it's going to damage their tokamak. On Mast, it doesn't damage the tokamak significantly, but you can see the interaction with the material surfaces at the top and the bottom. When we go to a future power plant, and ITER in particular, but also STEP, we have to learn how to get rid of these things. But notice the similarities between these big filamentary things coming out of the plasma and the sun. There are some similar similarities in the physics and some differences. So STEP, I'm just going to walk through in the last 5 minutes. I'm just going to walk through what does STEP look like. So I've told you a bit about the plasma physics, a bit about how the conditions we have to achieve, a bit about how the tokamak does it, a bit about a spherical tokamak. STEP is a spherical tokamak, so you can see it's the same sort of shape as Mast, but it's much bigger. If I was a giraffe and I stood in there, that's how big I would look. So you take Mast Upgrade and you scale it up to a bigger machine. Then let's look at some of the components that are envisaged to go into STEP. So STEP is aiming, I should have said actually before I went to this, so the main aim of STEP, let me just step back a bit. I'm going to see my time running forward. I was getting worried. So what STEP is aiming to do is it's targeting operation from 2040. So we're still designing it, haven't started building it yet, targeting operation around 2040. And the idea is that it will demonstrate net energy, so net power to the grid, okay, at the 100 megawatts electrical power level, and it will demonstrate that we can breed this tritium, going right back to the diagram that I showed you right at the beginning. That's what we're aiming to do with STEP. At the same time as building the skills in the community, in universities, in schools, etc. So we have the workforce to be able to operate this device in 2040. So it's going to be you guys operating it, not me. I'll be sitting in front of a fire with my Labrador and my pint by my hand by this time. You guys are going to be operating it. Really exciting career. Okay, so it's bigger than a giraffe. We've just done that. So let's have a look at the coil. So we talked about the coils. So you're familiar with the coils that are used for confining the plasma now. In STEP, these will be high temperature superconductors. So when I was just starting out in fusion back in the late 1980s, people just discovered these high temperature superconductors as a material. They are now just becoming available over the last 5 to 10 years in a form that allows you to build magnets out of them. And although we call them high temperature superconductors, it means that they're not liquid helium. They're still cold. They're still at 70 Kelvin or minus 200 centigrade kind of thing. But that's not so much the issue for us, that high temperature. The point is that you can operate these in superconducting form at higher magnetic fields. So we have the opportunity here with this new technology, these high temperature superconductors, go to much higher fields than we could go to before. And that again helps to create, as we think, a better magnetic bottle, and so increase that confinement time, and so be able to improve the triple product without going up in size. That's one aspect. The next thing is the diverter. And so this diverter is looking to capture that heat. So remember that exhaust pipe that I showed you, that magnetic exhaust pipe I showed you in that plasma, funnels all the heat into the top and the bottom. We make use of this box-like structure, which we've been testing on master upgrade, the tokamak that operates here now at Culham, and we think that will work really well. So that's built into the diverter of STEP. And then we have the blankets around here. Now, these blankets are really difficult things to engineer because they get the full force of these neutrons. These neutrons are flying into them. By definition, the neutrons have to capture the blankets have to capture those neutrons. So you can't shield the blankets. They've got to be captured in there. And so building these blankets and designing these blankets to be able to breed the tritium, get the heat out and convert it to power to take onto the grid, they are really big engineering feats. But it's much more than building a plant. There's a whole reason why the UK actually is in a world-leading position to deliver fusion. This here just shows one of them. So JET until it started decommissioning last year, was the only tokamak operating into which you could put tritium. As I said, we don't normally put tritium into a tokamak. We normally just operate with deuterium and demonstrate we can get the fusion conditions. And JET is the only one that's been built and designed to operate with tritium. That means it gives us a few skills in the UK. One of them is everything has to be done robotically with these robots. So we are world experts in the UK at designing these fusion-specific robots for the remote maintenance. Also, we have expertise of operating with deuterium tritium plasma. So for most of JET's life, JET was a European facility, and we, the UK, operated JET for the European community, and in fact the international community even beyond Europe. And so we have unique capability in operating with DT plasmas, deuterium tritium plasmas. But not only that, but with operating in something that was as closest thing we've got to an industrial scale fusion device, but also understanding how to do the tritium management. We operate master upgrade, so we know how to operate a spherical tokamak. We have this fancy new plasma exhaust capability, and we understand a lot about materials, both at UK Atomic Energy Authority, but also across the universities, and how materials respond to the neutrons, and how we can design the materials to respond to neutrons. But this is a big research area. We haven't solved this problem, just like we haven't fully solved the plasma physics problem yet. So big materials research is a big thing. And as I said, JET is presently being decommissioned. And if you think you learn as much about building something by taking it as apart as you do in designing it, we are learning a lot about JET as we take it apart. Decommissioning JET is itself a research project. So that brings me to my conclusions. So the points that I hope I've got across to you is that actually we have made great scientific progress over the years. If you look back at what's been achieved over the 60 years, it's a huge amount of progress. And this has taken fusion into the commercialization era. You hear it in the UK with the STEP program, but you'll hear it in private industry in the UK with First Light Fusion, for example, with Tokamak Energy, for example. You'll hear it in the US, all the private fusion companies coming out in the US, across Europe, across China. There is great, and so fusion really is now being moved into the commercialization era, where I am pretty confident that you guys will see it in your lifetime, putting power to the grid. But it's not simple. We still have science and technology research questions to address, and we've got to address those in parallel with doing the engineering design for these facilities. And that actually gives other great opportunities that are companies with those challenges. The tokamak is an attractive pathway, but it's just one pathway. There are others, and actually, if you want to ask questions, I'm happy to try and answer them about the other pathways, but it is a particularly attractive pathway, and that's the one that we're pursuing here at UK Industrial Fusion Solutions and with UK Atomic Energy Authority as the key partner. And we're doing that through STEP, Spherical Tokamak for Energy Production, and we are aiming to complete the STEP prototype plants, which will demonstrate the pathway to commercialization, and that plant should be ready and operating by 2040. It will be built on a site in West Burton, on an old coal-fired power station site, which is where I'm usually based. I'm down at Culham today for this seminar, for this webinar, but I'm usually based in at the site where STEP will be. It's just north of Nottingham, basically, about 30 or 40 miles north of Nottingham. And then this will be followed rapidly within 10 to 20 years of the first of a kind commercial plant, and then a whole fleet beyond that. So that brings me to the end. Sorry, I've overrun by 2 or 3 minutes, but I hope you will forgive my excitement. I'll stop sharing now.
Oh, thank you very much, Howard. That was really interesting. There's quite a lot of questions that we've come in. I'm going to start with, I don't know if it's an easy one or a really difficult one, but how did you get into nuclear fusion slash plasma physics?
So I've always been interested in physics. I did a physics degree. I did a particle physics PhD, and particle physics is really exciting. Again, it's big science, and it's worthwhile because there are lots of applications and it's pushing the frontiers, but it's not really applied. I couldn't. I was frustrated by the fact that I couldn't see how to use the physics to do something that was directly beneficial to society. And that's when I did fusion. That's why I got into fusion. I did it as an undergraduate project when I was an undergraduate at Durham. And then I saw fusion as a big science, big complex science, difficult problems to solve with a really major potential for a really major impact on society, and not just society in the developed world, but also the developing world as well, and trying to make energy more uniformly accessible across the world. And energy is what powers our societies in so many ways. If you just think about the challenges that we face if we ever start running out of society, out of energy, and the political imbalances that it can create if we don't have enough energy, it is a real driver for our quality of life in so many different ways.
Thank you. Right, so maybe more onto some sciencey type questions. So this is somebody's asking about lithium. So are there potential future problems with the supply of lithium going to drastically affect the ability for the development of fusion for these power plants, i.e., because we're using more electrical devices?
Okay, so I think probably we will find that one of the biggest users of lithium will be electric vehicles. And at first sight, you might think, oh, well, that's pretty big competition. How on earth are we going to have enough lithium to compete against electric cars? I have, but then think back to what I said. The lithium in one laptop battery is enough to give me my lifetime's electricity needs. So I don't actually need very much lithium. As I said, I also drive an electric vehicle. That's got loads of lithium in, much more lithium in it than my laptop battery has in its battery, I assume. And so actually, the amount of lithium that we need compared to the lithium that needs to go into an electric vehicle is a tiny amount. So given the importance of it, I think, we will scrape off, even if it's 10% of what's in the electric vehicle market, we will take off that 10% and it would go into the energy market. So I don't think that will be a challenge. If anything, it will drive the supply chain of lithium and make lithium more available for fusion.
So Alana has asked, how can you control plasma instabilities in a tokamak to sustain fusion?
Oh my word, that's a brilliant question. Have you got a day or two? Let me give you a really neat one, because I can go back to that picture. Remember the picture with the big plasma eruptions that were coming out? That was a real mass plasma, and they were real eruptions, those big filamentary things. The way we do it there is we put a whole bunch of coils around the edge of the plasma, and these are called resonant magnetic field coils. Everything in fusion, almost everything in fusion, that in my world of fusion anyway, is related to magnets and coils. And so you put these little magnets around the edge. And what those magnets do is they put a little ripple in the magnetic field that's confining the plasma. Because if you think what's happened, remember what I said happened? You had these wispy filaments initially, and they give you the turbulence, and they hold the pressure gradient low because you've got so much heat. The heat is coming out of it too fast. So they hold the pressure gradient low. When the plasma went sharp, that the turbulence at the edge was suppressed, the pressure gradient went up, and it went so big that the plasma goes pop and relaxes back down again. Then the pressure gradient goes back up again, the plasma goes pop and relaxes back down again. So actually, the confinement's got too good. We've got into a place where it's popping. And so we just want to relax the pressure gradient back down again. And we think you can do that by putting these magnetic fields around magnetic coils around the plasma to ripple the magnetic fields, deliberately degrade the confinement at the edge to relax that pressure gradient back down again and switch off those instabilities. Works beautifully on tokamaks like D3D. On massed upgrade, it works a bit, but not fully, and we don't fully understand it. And the reason we don't fully understand it is because it's not the magnetic field that you're applying that counts, it's the magnetic field that gets into a plasma. And if you know about conductors, it's hard to get a magnetic field into a superconductor, and a plasma is a really good conductor. So the challenge we've got to do is understand how to get that magnetic field to go into the plasma and to relax that back down again. That was quite a long answer, but nowhere near as long as it could have been.
I know it's your
I
specialist
love it.
subject,
It's
right?
what I do. Well, it's not what I
Uh,
used to do.
right. So you mentioned how you are still designing STEP. Someone was wondering about the design process because obviously you can't create prototypes as easily. And so how would you know if the design works? Would you rely on computer simulation?
Absolutely brilliant question. This is absolutely fundamental in my view, because you can't recreate fusion conditions. Those neutrons that come flying out and impact the materials and have and change the materials' properties, those are really fast neutrons. Now you get neutrons in a fission reaction, but they're slow neutrons, and so they do damage. And you can learn things by putting materials into a fission reactor. But the kind of damage process are different to the process you get from a fusion reactor. You can also, and the problem is you can't accelerate a neutron. It hasn't got a charge. You can't, if you apply an electric field, it doesn't feel it. So you can't accelerate a neutron trivially. You can accelerate a charged particle though. So what you can do is you can use the fact that a proton is about the same mass as a neutron and instead accelerate a proton and bash the protons into materials with that energy. But then you're bashing a material with a charged particle, which behaves differently to a neutral particle. Charged particle will only go in like a few micrometers, whereas a neutral particle will go in like half a meter or so. And so it's different processes, but you can learn things from those. You can learn about the physics processes, and then you combine that with simulation to check that you understand the physics processes, and then you use the simulation to understand actually, well, what would happen in a fusion environment for the materials in a fusion environment. So that is one example. And actually, if we're going to deliver STEP by 2040, the only way we will do it is by having many situations like that where we augment physical test models and with a physics-based simulation capability of that physics to be able to predict what will happen in the material. Simulations, computer simulations are absolutely key, and it's a key part of the STEP program. And we don't yet have all the answers. How to optimally do that? How to optimally, I kind of think about it, you've got these physical prototypes as a traditional way of doing engineering design. And now we have the opportunities for building virtual prototypes. How do you optimally mix those things together to give yourself confidence that what you're predicting is the real world, and therefore you can make people comfortable that the machine will act the way you think it will.
Thank you. So someone's asked, what are the advantages of magnetic confinement compared to inertial confinement? And I would like to ask, what's the difference between achieving, this top energy production in magnetic confinement, and how far away is inertial confinement to that goal?
So inertial confinement is measured So I'm not an expert in inertial confinement. So take what I say about inertial confinement with a pinch of salt, and please ask an expert like Kirsty. So so I think so inertial confinement, you're taking a small pellet of fuel and you're basically compressing it with lots of lasers. That's the fundamental idea. But one of the big challenges with inertial confinement is how you've got to make that pellet incredibly smooth. It's a huge manufacturing challenge to make those, and you've got to be able to shoot them 10 times a second. So that's how many pellets you need, and they need to cost a few pence. At the moment, they're like tens of thousands of pounds to create one. And so that's a big challenge for the inertial fusion, is how to scale that up and reduce the cost. Then you've got the laser, and making that laser that compresses the pellet has to be much more efficient than they are at the moment. Now, there is a pathway. I don't rule it out. I absolutely don't rule inertial fusion out. But I think some of the technological challenges they've got to make it efficient are bigger than they are in the magnetic fusion case. Absolutely, it should continue. Energy is really important, and so absolutely we should be pushing forward everything we can. And there's sufficient optimism and hope that we will find a solution for inertial fusion one day, that we should be pursuing it. Magnetic fusion is not perfect. It has got challenges. So with a tokamak the biggest challenge I think we've got with a tokamak is being able to manage what we call a disruption. So tokamak, you can see that it's right on the edge of working a tokamak. We're so close, having come so far. You can see how tantalizingly close we are with it. But that last bit, it gets harder and harder and harder as you go on. And one of the big challenges that we have is with the disruption. Remember I said there's a plasma current flows through the plasma, and we've already got a magnetic field. That plasma current is a few megamps, a few million amps. Magnetic field is a few Tesla. You're dealing with component size of about a meter or so across, or more than a meter or so across. If you suddenly lose your plasma, if you suddenly lose control in what we call a disruption, those millions of amps of current suddenly start flowing through your vessel components. Now you've got conducting vessel components carrying millions of amps in a field of Tesla that are a meter or so across. That's forces of millions of newtons, millions of newtons. You try and find forces of millions of newtons. You're looking at big jumbo jets. Dropping a jumbo jet is like a million newton. Now, those forces can make jet jump, and jet didn't go. It did jump. It jumped a few centimeters one day with a disruption like that. And now we're going to ITER with twice the currents, twice the field, twice the size, 8 times the force. And so disruptions are a real concern, and be able to manage those. And we have solutions. We have solutions for them. So I don't want to say it's a showstopper, but that's one of the big risks with a tokamak. So there are risks to both. Hold my hand up. It's risks to both. Nothing's perfect, but I think we'll solve those problems, those past problems. And if there were no problems, you guys wouldn't have any research to do in the future. So it's good that there's something for you to do.
Right, so we're kind of running out of time, but I'm going to combine two questions here. So what technologies are used to keep the plasma at such hot temperatures? And then the second question is, how was the plasma filmed at such high temperatures?
Oh, okay. They're both cool ones actually. So first of all, the heating. So in the heating that we will use, there are a number of ways of heating a tokamak plasma. The one that we're going to use on STEP is basically microwaves. Same technologies you have at home in your oven, but where in your oven it's a few hundred watts, we're looking at a few hundred megawatts. So hugely more power, like a million times more power than you guys have. How does that heat the plasma? Well, basically what you can do is you're firing a microwave is just an electromagnetic wave. You fire that wave into the plasma, and that plasma, and because your electron is charged, it feels that wave, and so it oscillates up and down with that wave. Now, just like a surfer, if a surfer feels a wave go under them and they don't try and match their speed to the wave, they'll just bob up and down as the wave goes through. They're not tapping the energy of the wave. But if they match their speed to the wave, they paddle along, they say got resonate with the wave will pick them up and they will tap the energy of the wave and it will take them into shore. Same thing with the electrons. We match that frequency of that microwave to the frequency the electrons gyrate around the magnetic field. They then pick up the energy and that heats them up, transfers the energy from the wave to the plasma, and that heats them up. So that's the first one. The second one I'll try and do more quickly. An actual plasma, you don't see. It doesn't emit any light, and the reason it doesn't emit light is one of the reasons you get a light from a gas is it's the electrons in their various energy levels. If you heat them, they go to a different energy level. As they relax back down to an energy level closer to the nucleus again, they emit light. Now, as I said to you, a plasma, you've taken those electrons away. There are no energy levels that the electron sits around with around the nucleus. There are other ways that it can emit light, but not in the visible frequency for the plasma. So a really good plasma is absolutely dark. Then you go, well, I saw it. I saw the edge. Well, that edge is the neutral particles, the neutral gas around the plasma. And those filaments that you saw are actually filaments of plasma shooting out. And you don't see the filaments of plasma shooting out. You see the filaments of plasma interacting with the neutral gas around and lighting up the neutral gas around. And it's that light that you're seeing. And it's just visible light in this case. But you can look at other frequencies with fancy bits of kit. And again, Kirsty knows more about this than me.
Right, so I think we're going to have to bring the questions to a close. So thank you very much, Howard. I would say, because there are quite a lot of questions, please, if you're a student who is participating in the master classes, feel free to post these on the online question forum there. The recording of this event will be made available on the Nuclear Masterclass website next week, and a link will also be emailed to all the ticket holders. Next week's webinar will explore nuclear medicine and using radiochemistry for both imaging and treating cancer. We hope to see you, many of you there, and thank you all for joining us, and I hope you have a good evening.